Now, just to remind you that electron volt is 1.6 into 10 to the power minus 19 joules, right. Now, if you want to express 1 electron volt in terms of kBt, kBt of room temperature, right, then you would say that so 1 electron volt is 1.6 into 10 to the power minus 19 into 4.2 into 10 to the power minus 21. Do the calculation and what you get is 0.38 into 10 to the power 22 kBt 300, right. If you change temperature, the value of kBt is going to change, remember that. So, a question would be, so we are discussing units, and at what value of temperature is kBt equal to 1.6 into 10 to the power minus 19 joules, 1 electron volt, and if you calculate that, that is essentially this calculation 1.6 into 10 to the power minus 19 by kb, and what you get out of it is approximately 11,000 Kelvin. It is a really high temperature, everything would melt and vaporize at that temperature. Okay. So, the point I am trying to make is we can't be working with different units. What we are going to do is measure kBt or the thermal energy, the temperature. You divide kBt by kb, you get the temperature. We shall measure kBt in units of J, J being the coupling constant minus J SI dot Sj. What does it mean by that? Now, suppose, just suppose that for a particular material which can be modeled by the Ising model, say J is equal to minus 0.05 electron volt, say, and we say J equal to 1. So, we measure energy in units of J. So, we were measuring it in terms of electron volts, we say that we are going to measure energy in units of J, where J has the value 0.05 electron volt. Then what would we get? 0.1 electron volt, we will call it 2 J. J has been set to 1, but I mean suppose J equal to 0.05 electron volt, then 0.1 electron volt equal to 2 J. 0.3 electron volt equal to 6 J. Similarly, we can measure kBt. So, here what were we doing? We were measuring some unit of energy, electron volt, in terms of J. We can measure kBt in terms of J. So, you can say that kBt equal to 2 J, say, or kBt equal to 0.2 J or 5 J, and so on, right. So, what does it mean to say that kBt is 2 J? If kBt is 2 J, it means kBt equal to 0.1 electron volts, and from there you can basically get the value of T to be 0.01 electron volt by kb, which will give you the units of temperature. Okay. With this background, where we have set all the units, all basically the Bohr magneton, H cross, etc., are sitting inside the J. We are basically going to measure magnetization in terms of spin +1 and -1, and we are going to measure the temperature, the thermal energy. So, I am using this equivalently, but kBt is thermal energy, T has units of temperature, but you take thermal energy divide by kb, you get T. We shall be measuring temperature in units of not electron volt, but in units of J, where we shall set J equal to 1, and then figure out at what temperature, at what value of temperature in units of J does the system, an Ising model, get demagnetized or loses its ferromagnetic behavior, at what value of temperature do we get that. So, that is basically where we are heading. Okay. With this background, let us start looking at the actual computer code. All this discussion that we have had, how do we actually implement it, and then when you see results out from the code, we are going to discuss this, look at the effect of thermal fluctuations, thermal energy. You will have a better understanding of what I told on this screen, right. So, let us actually head to the actual computer. Now, basically the name of my code is Ising.F90. Okay, so I am in the appropriate directory, and I am like to use the VI editor. You can use Emacs or whatever is a editor of your choice, and I shall show you the code GI Ising.F90. Okay, it's a program, it's a Fortran 90 code. Its name is Ising, program Ising. I have defined implicit none, which is a safe thing to do. So, basically you do not end up doing any miscalculations. All the variables you have to define by hand and to do your calculations. Here I have defined some variables I, j, l and so on so forth, which I shall use basically to count dummy variables as we go proceed, choose different spins of the lattice or to monitor the number of iterations and so on so forth. What is important is you can give them I, j, k, l whatever you want, integers typically. Here L is essentially L is the size of the lattice, which one shall read here. Okay. So, you can read L and change the size of the lattice, which we shall be using. The other important quantity is niter, is basically the number of iterations that it will be running at a particular temperature. So, at the moment we shall need to understand how these thermodynamic quantities fluctuate due to at a particular temperature. Later we will be calculating the phase diagram. We will keep things simple by simple and calculate things one by one, increase the complexity one by one. That is what I mean by that. And the quantities of interest are T equal to 2. So, I have set temperature T equal to 2, where J Ising, which is the same as J when we were discussing it on board, is essentially I was set to 1. I can change temperature to 2.1, 2, 2.5, 0.3. So, you are basically changing temperature in units of J, as I discussed previously. Okay. So, you have to give a random number seed here. Okay. And the spins +1 and -1, I am basically defining an array whose size is allocatable, and the name of that variable 2-dimensional array is spin. Here I give 2 colons, which means it is a 2D array, and its size shall be discussed when we implement, when we run the code. Okay. So, here I am saying okay, please give the number of lattice points in one dimension. So, that is L. You can give L to be 20, 30, 40, 5, 10, whatever you want, number of iterations that you want at that particular temperature, and we shall first do this and see how thermodynamic quantities evolve. Once you have given L in the system, you have to allocate this array. Say that the spin is the spin variable, the spin array is L cross L. Then you set the initial energy to be instantaneous energy of the system. This is basically defining variables, energy to be 0. This is the energy of the system. Now, this is not the thermodynamic energy, this is the instantaneous energy of when you generate a microstate with a particular configuration of the spins. What is the energy of that lattice, of that particular configuration of spins or that microstate? You have to average over different microstates to get the thermodynamic average. Remember that, right? We shall do that later. So, E has been set to 0. The magnetization, not the thermodynamic magnetization, the instantaneous magnetization. what is the, if you sum over all the spins, some are plus, some are minus, if you sum over all the spins, what is the total magnetic moment, what is the total value of the spin of the lattice, that is what M is measuring, the instantaneous magnetization of the lattice, right, instantaneous value of spin of the lattice. Here I have defined N, the total number of spins, to be L cross L, L being the number of spins along one particular direction. Here we am calling a random number seed basically to generate a set of random numbers. And what is the first step in the flow chart? If you go back in the video and look at it, one has to initialize the lattice. What does initialize the lattice mean? Give the values of the spin plus 1 or minus 1 at each lattice site, and that is exactly what I am doing. So, here you see that do I equal to 1 to L. So, the value of I changes from 1 to L, right. Do j equal to 1 to L. So, there were two indices x and y corresponding to x and y. So, I and j. So, each varies from 1 to L. Then you are generating a random number here called random number r. The random number is stored in this variable r, and here I am choosing a random initial configuration, which means that you go to each site in the lattice and with equal probability you assign the spin at that lattice point, the value of the spin at that lattice point to be either plus 1 or minus 1, right. So, how do you do that? You basically generate a random number r, and if that random number r is less than 0.5. So, random number r will be generated, I am using a uniform random number generator, which means that the random number generator will have a uniform probability to be generated at any value between 0 and 1, right. So, the 50% of the time the random number will be less than half, and half if you generate another random number, the probability that its value will be greater than 0.5, half is again half. So, if r is less than 0.5, then you say okay, give the value of the spin variable spin j I. So, one particular lattice site and j and I are varying, do I equal to 1 to L, do j equal to 1 to L. So, if spin j I here, if this condition r is less than 0.5, if this condition is satisfied, then spin of j I is given minus 1. If it is greater than 1, as I said, equal probability of being either plus 1 or minus 1, then you give it plus 1. So, on an average, half of the spins in the lattice will be pointing up, half of the spins on the lattice will be pointing down, right. So, you have assigned spin values to this. You want to see whether you have done it right or not. For that, what you do, you can write down I as you change the lattice site, j, and basically this, why I have given this you shall understand later. I mean, this basically later for visualization. So, it is a dummy variable which I have defined to be 0, and float spin I j, I have whatever value has been assigned here or here, I am writing it down. So, you can actually, after you have initialized the lattice, you can go to basically any lattice size which is specified by I and j and check what the value of the spin has been given, right. And that I am writing down in a file and 71, which has been initialized just before this loop. So, open files 71 file equal to initializing.dat. Initializing.dat means essentially that you are writing down the initial spin configuration of the lattice in this file, just for a cross check whether you have initialized it appropriately or not. As I told you, our thermodynamic properties are not going to depend upon the initial condition. You have to evolve the system by suitable Metropolis algorithm to equilibrium. Also, to choose a initial configuration where all spins are pointing up or all spins are pointing down. Initial configuration does not matter. Here I have simply chosen to give all spins to assign spins at different points in the lattice randomly, half pointing up, half pointing down. But if you suppose wanted to basically say, okay, I want to look at all spins pointing up. So, if you wanted to give all the spins of the lattice to be say +1, so that they are all pointing up, or -1 if they are all pointing down, then what you can simply do is comment out this part and do this. So, do I equal to 1 to L, do j equal to 1 to L. So, it systematically, so what the code will do when you run it. So, it will go I equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and corresponding to j equal to 1, and then j will also change. So, basically you are scanning over the entire length of the lattice through this, and every lattice site, at every lattice site the spin variable is set to -1 here. You can equally do it +1, does not really matter. So, here then all spins are now pointing up. I am just saving this one by colon w, right. So, this is your initialization of the lattice. Now, what do? You calculate the initial magnetization or the value of the total number of spins of the system and the energy of the system. Okay. So, to calculate the total energy and magnetization of the lattice, the initial one. So, what we do is again do I equal to 1 to L, do j equal to 1 to L, which means that you are essentially going to each lattice site, you are scanning over each lattice site, the spin at each lattice site, and here we are identifying the neighbors. So, basically if you are, so suppose you have a spin whose location is spin I comma j. So, a equal to I plus 1, which is basically the right hand side of your the spin on the right hand side of your target spin I j, b equal to I minus 1, which means on the left, c equal to j plus 1, which is basically on the top of your lattice site I j, and d equal to j minus 1, which is at the bottom of the lattice site, right. And now, basically if by chance I equal to L, which is basically if you the spin under consideration is at the boundaries, then its right hand neighbor will be basically the other side of the lattice by periodic boundary conditions. So, that is why I have written if I equal to L, then A, which is the neighbor on the right hand side, is essentially equal to 1. Similarly, if I equal to 1, which is on the left boundary, if the spin in under consideration is on the left boundary, then the neighbor which is to the left of this one, so on the this side is equal to L. It is basically periodic boundary conditions which we discussed in the past. And similarly, these two conditions, if j equal to 1, which is at the top boundary of the lattice, then the neighboring spin on the top of it is L, and so on and so forth. This is on the other side. Now, you have basically identified the 4 neighbors of spin I j. Even if I or j lies somewhere on the boundary, periodic boundary conditions have been invoked. We have correctly identified the 4 neighbors of any spin on the lattice I j k L, wherever be it on the lattice, and m, which had been set equal to 0 before the beginning of the simulation. I am saying m equal to m plus spin I j. So, the value of the variables m, you are adding the value of the spin at a particular site, and you are going to each lattice site and adding the value of the spin at that lattice site. If all the spins are pointing up, then basically at the once you have scanned the entire lattice, you are going to add 1 every time you visit every lattice site, and then the end of the loop here you will have the value of m to be n into 1, 1 being because all spins are up. However, if you started with a random initial conditions, then some of the spins will be up and some of the spins will be down, and the value of this m, the variable m, will be, you are adding sometimes +1 to it, sometimes -1 to it with equal probability nearly. So, it the value of m after you have scanned through the lattice will be some number close to 0. Okay. Similarly, you can calculate the value of the energy of the lattice. So, you have been going to each lattice site, E had also been set to 0 right at the beginning of the code, and now you are doing minus j Ising being equivalent to the j, the energy scale of the problem, and then spin j I. So, you have to do the multiplication S I S j, sum over all neighbors, and that is exactly what has been done here. Spin A j, spin B j on the 2 neighbors on the left and on the right of the spin I j, and this is the spin on the top and at the bottom neighbor of spin j I. So, I have multiplied spin j I by the spin values of the spin at the lattice sites on the top, bottom, left and right, and by that you get essentially the value of this energy for a particular spin j I. Then of course, you go to the next lattice site and again identify its neighbors, calculate the energy of the interaction, and you add it to E. So, I am saying add, though there is the minus sign here, because the Hamiltonian itself comes with minus j summation S I dot S j, and that is all that I am implementing here. Here what is done, mag is essentially the magnetization per spin. When I say magnetization, I mean the instantaneous magnetization, the magnetization of a particular microstate, the value of the magnetic moment of a particular microstate, right. So, that is m divided by float n being the total number of spins in the lattice. That is trivial, but what is not so trivial is the value of the energy. So, here I have multiplied the value of the energy of the microstate of that spin configuration by half. Why this half? Because as I go from each lattice site 1, 2, 3, 4 and so on and so forth, I calculate the energy of interaction between 1 and 2. And then when I go to the next lattice site, I again calculate the energy of interaction between 2 and 1. Because if something is the right neighbor, if 2 is the right neighbor of spin 1 say, then spin 1 is the left neighbor of spin 2. So, every energy has been double counted in this calculation. If you just think about it, you will figure it out, and since to basically correct for this double counting, I have multiplied it by 0.05. Then what am I doing? I am saying okay, write down the total initial energy and energy per spin on the screen, and we shall see that when we run the code. Here I have said write down the initial magnetization, initial magnetic moment, not instantaneous magnetization of the entire lattice, and m per spin. So, I have just written down m mag E and E by float n. Okay. So, this is initialization complete. You have already access to all the spins which have been initialized on a lattice. Moreover, you have calculated the initial energy of the entire lattice for that microstate. You have calculated the initial magnetic moment or the spin, the total spin of the lattice at time t equal to 0 before the simulation starts, and you have also access to the magnetic the spin per lattice site and the energy per lattice site. So, the next thing to do is basically evolve it to equilibrium. For that you do start Monte Carlo steps, and here you see that I have a loop which says time equal to 1 comma niter. Time is a dummy variable, you can call it by any other variable. We are essentially doing ensemble average, but we are generating one microstate after the other using the Metropolis algorithm, which is implemented below. And we are saying okay, we are going to have a niter, number of iterations. Niter stands for number of iterations, n iter. We are going to have n niter number of independent microstates. That is what we are going to generate after every Monte Carlo step. Okay. So, we are actually going to generate more, but now do equal to 1 to L, do Nn equal to 1 to L. These are and Nn are dummy variables. We are basically going over each site in the lattice, but we are not going through each site in the lattice in a sequential manner. Why and how? Well, the how first. So, we are generating a random number here r and another random number r. We are multiplying it by the length of the lattice float L. So, basically what you have I here is I am choosing a random lattice site. So, generating a random number between 0 and 1, multiplying it by L. So, you have a random number between 0 and L, they will take the integer, and by doing a plus 1, and you should think why I am adding a plus 1, or if you delete it what happens. I am basically choosing a random coordinate in the x direction, and here I am choosing a random coordinate in the y direction. So, I am choosing a random lattice site I and j. We are identifying the neighbors just as we did previously. Here we are again implementing the periodic boundary condition in case I or j is set on the boundaries of the lattice, and here we are calculating the initial energy for spin I j for a particular value of spin, and the formula is exactly the same as previously, except we were adding the energies previously. Here I am just looking at the energy of a particular spin I j and the energy with its neighbors, right. Now, as we said in the Metropolis algorithm, we give a trial flip. So, if the spin was pointing plus, you say okay, let its spin be minus 1, and if it is minus 1, then you give it a trial flip of plus 1. So, here I have given a minus sign, whatever be the value of spin I j, I have given a minus sign to it, and with this changed flip and the changed value of the spin after the spin flip, I am calculating the new value of the energy of that configuration. So, I am talking about the spin I j and its 4 neighbors, right. So, E I stands for initial energy, E f for final energy after the trial spin flip, and here you calculate the difference in energies, d E equal to E f minus E I. Now, as per the Metropolis algorithm, as we discussed, if d E, this change in energy due to the trial flip, if it is less than 0, if energy decreases, then basically the trial spin flip is accepted with probability 1. So, if so here I have already done the trial spin flip. If d E is less than 0, the change in energy is negative, then you update the total energy of the system. The total energy of the system was E, the difference in energy was d E. So, I have written the new energy after this trial spin flip, which has been accepted, is the new energy is E plus d E, and the new magnetization of the entire lattice, m was the instantaneous magnetization of the entire lattice, that is m plus 2 float spin I j, right, plus 1 goes to minus 1. So, the change in spin of the lattice is plus 1 minus 1. So, that is why 2, right. So, that is how you get this, but so basically you have accepted the spin flip here in these 2 steps and updated the total energy of the lattice and the total instantaneous spin state of the lattice. But if d E was greater than 0, or so here just notice that this is less than equal to 0, but if dE was greater than 0. So, this is this else condition for that, then you are supposed to accept the spin flip with probability delta E by kBt. So, how do we accept spin flip with probability e to the power delta E by kBt? If you remember Prashanjit's lecture about cumulative distribution, I am basically and about random numbers and so on so forth, I am using that idea. So, here I calculate u being a dummy variable is exponential minus del E by kBt, kB has been set to 1. So, basically here what ideally it should be is kBt, but I do not need an extra variable kB which has anyway been set to 1. So, I have just written dE by t. Call a random number h. If h is less than u, this is what is u, that is e to the power delta E by kBt, then accept the spin flip. Then you again update the value of E and the value of m just as was done in these two steps, and the spin is already been trial flipped here. So, then that step is accepted. However, if this condition is not satisfied, if this random number is greater than u, then this spin flip is not accepted. I put the spin I j to be minus spin I j. So, suppose there was a positive spin, I had given a trial spin flip to be minus 1. Now, I say okay, this trial spin flip is not accepted, then I have to put it back to plus 1. So, that is exactly what I am doing in this step. Okay. And of course, I do not need to update the m and the E. Now, this is being done this. So, there are now n attempts, n being L cross L attempts which are being done. So, you are randomly choosing spin n times, trying to flip the spin. Sometimes it is accepted, sometimes it is not, depending upon the value of delta E and especially kBt, the thermal energy. And at the end, once you have done it for essentially n times, you have completed one Monte Carlo step. These two n-dos correspond to these two n-dos, right, and it has been written in a manner so that these n-dos and n-diffs can easily be identified. This is the way you write programs, so that you do not get lost between n-dos after 100 lines and dos and n-dos, ifs and n-diffs after 100 lines. So, that is why you basically structure the writing in the way it has been done here. And after one Monte Carlo step, that is n attempts, you write down the total magnetization, instantaneous magnetization per spin, and the energy of the system per spin in a file essentially, right. So, this file is file number 10 and it had been opened right at the beginning here. So, Ising T2 and 40 init random. So, this says that the temperature is 2, the lattice size is 40, actually it should be L not N. So, it is a 40 cross 40 lattice and with initial random condition, right. So, now if you do this knitter times, then you have this loop was here, loop over Monte Carlo step, and that loop ends here, and these then you would have got the energy and magnetization, you would have written it down after every Monte Carlo steps knitter times, and you can set knitter to be 1000 or 1 lakh or 1 million, it is your choice. A question. So, just to remind you that the spin to be updated is chosen randomly in the lattice. In one Monte Carlo steps, you are doing n attempts to spin flip, but the spin to be chosen to be given a trial flip is chosen randomly. As a consequence, in one Monte Carlo step, it is quite possible that 1 or 2 of the spins or 5 of the spins you have given trial flips more than once. On the other hand, a few particular spins have not been given at all a trial flip, which is possible because you are choosing the spins randomly. But in the next or the next Monte Carlo step, the ones which have been left out to give a trial flip, you might choose that twice, and the ones which basically you attempted a spin flip twice or thrice in one Monte Carlo step, they will be basically this time left out, and the ones which were previously left out, they might have 2 attempts. Now, if you have many Monte Carlo steps, on an average, and if you have a good random number, then on the average all spins, the number of attempts to flip a spin will be accepted equally. Okay. If you have just 5 Monte Carlo steps, of course, some spins are not going to be updated, some spins are going to be updated more than once, or at least try attempt to make a spin flip will be more than one. But if you do it over say 10,000 or 1,000,000 Monte Carlo steps, then on an average each spin will have an equal attempt, or each will have an equal number of trial spin flips. Now, whether those trial spin flips are accepted or not, that will of course depend upon the temperature. How? Well, to do that, just we have to actually run the code and see, as you change the temperature, as you change the lattice site, what happens, and that is exactly what we are going to start doing in the next class or tutorial. Thanks.